Now let's talk about the effusion and diffusion of gas. In a previous video, we calculated the average speed of ammonia at room temperature and found that it was in excess of 1,000 miles per hour. It means the molecules are traveling very fast. But let's think about what would happen if I were to open a bottle of ammonia gas. If I were to open a bottle of ammonia gas, you would think the molecules are coming out at 1,000 miles an hour, and so every single person in the classroom should be able to immediately be able to smell the ammonia. But we know that to not be the case. We know that it would take time for the ammonia molecules to diffuse throughout the entire room to where everyone would be able to smell it. So why does that take so long? What makes diffusion so slow? What is it that's keeping the molecules from making their way across the room? Keep in mind that the room is not completely evacuated, right? So it's not like there are no other gas molecules in the room. The room is full of other gas particles from our atmosphere, and collisions between the ammonia gas and the other gas particles in the room will make the process of diffusion slow. All those collisions will inhibit the forward progress of the ammonia gas. And we could take a look at a video that illustrates the process of diffusion and how collisions can slow the mixing of gases and the forward progress of gases throughout a sample. In this video, you can imagine the ammonia gas as being the yellow particles and the rest of the atmosphere as being the white particles. And what you see is that although the molecules are traveling very quickly, all these collisions are slowing the progress of the mixing of the gas here, right? So that kind of helps to get a little bit of a visual of what's going on, hopefully. Additionally, it gives us even more reason why it's so important for us to understand collisions of gas particles, right? So I mentioned previously that collisions of gas particles can lead to chemical reactions, but collisions of gas particles also can slow the mixing of gases and the process of mass transport. That deals with a concept called diffusion as gases mix. There's another concept that we should talk about here called effusion, which is the process of a gas effusing through or passing through a barrier. So here what we have is a container that's been separated into two halves. One half has been filled with a gas. The other half is evacuated. There's nothing on the other side. There's a partition between the two containers and a small pinhole. And effusion is the process of the gas particles traveling through the pinhole into the evacuated side of the container. This again is another property of mass transport, which has a lot of very important implications in chemistry. The ability for a gas to effuse through a barrier. Now, the way that that's going to happen is gas particles, remember, they're moving around in straight lines from one collision to another. And so there's all these collisions happening, and then eventually there's going to be a possibility that a gas particle is heading on just the right trajectory that it's able to go right through the hole and into the other part of the container. Now, we can talk about rates of effusion for gases. And one thing that's commonly done is studying this by what's called Graham's law of effusion, which allows us to compare the relative rates of effusion for two different gases. Graham's law says that the rate of effusion for gas 1 divided by the rate of effusion for gas 2 will be equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. What we recognize here in looking at Graham's law of effusion is that it has the exact same functional form as the ratio of the average speeds for the two gases that we saw in our previous video. So it's interesting, I think, to see how the result that we got earlier can also be applied towards studying other things like the process of effusion. And because gases do effuse at different relative rates, this will allow you to maybe purify a mixture of two gases, right? Let's say that you have two gases and one is much heavier than the other, then the heavier gas will effuse much more slowly. And so you can allow the lighter gas to effuse very quickly into the other partition, and that helps to purify it, right? The lighter gas will effuse more quickly, and so you'll be able to concentrate the lighter gas on the other side of the partition since it's able to effuse through the barrier more rapidly. Let's do a calculation here. We're told that it takes 4.5 minutes for 1 liter of helium gas to effuse through a barrier. And first we're asked to calculate the effusion rate of helium gas in units of liters per second. So let's talk about how we would find the rate. To find any kind of a rate, we take the change that we're interested in and we divide it by the change in time. If you wanted to find the rate that you were traveling in your car, right? You would take the change in your position, or that's the distance that you traveled, and you would divide it by the change in time. The same sort of a thing applies here. So to find an effusion rate, we would take the amount of gas that effused, and then we would divide that by the change in time. And so the amount that effused, we were told, was 1 liter, and that happened in 4.5 minutes. So that's our time. And because we want to have the effusion rate in units of liters per second, right now we recognize this is liters per minute. We've got to convert the minutes to seconds. And we know how to do that because we know that in 1 minute, there are 60 seconds. So there's our conversion factor. We see that the minutes cancel out, and now we have seconds on the bottom. Our units are liters per second. The effusion rate for the helium gas will come out to 0.0037 liters per second. And there we have it. All right. Now, having calculated the effusion rate of helium gas in liters per second, let's now use Graham's law to find what the effusion rate would be for a different gas. Now we need to find what the effusion rate of chlorine gas would be under the same conditions. And so to do that, we're going to use Graham's law. Now, it doesn't matter what you label as gas 1 and what you label as gas 2. You'll get the same answer either way, but there are some ways to answer the question and set it up that are more convenient than others. To me, I think it's more convenient to define the chlorine gas as gas 1. So we're going to say that the rate for the Cl2 over the rate for the helium is equal to the square root of, since we said that helium is gas 2, then we're going to have molar mass of helium on the top here over the molar mass of chlorine, because we defined that as gas 1. The reason why I wanted to define it in this way is because now to find the rate of Cl2, all I have to do is multiply both sides by the rate of helium. I don't have to do a ton of other algebraic steps. So to isolate the effusion rate for the Cl2, multiply both sides by the rate of the helium, times the square root of the molar mass of helium over the molar mass of Cl2. Now we know what the effusion rate for the helium is because we found that in part 1 of the problem. We found that that was 0.00370 liters per second times, and again with these molar masses, because you're taking a ratio, it doesn't matter what units you use as long as you're consistent. But just for the sake of argument, I'm going to use units of kilograms per mole because we have capital M here. So for helium, that's 4 grams per mole, or that's 0.004 kilograms per mole, divided by the molar mass of chlorine, which is 70 grams per mole, or we could write that as 0.070 kilograms per mole. And again, if you just kept it in grams per mole, you get the exact same answer because the units cancel out. And what you find is that the effusion rate for the chlorine gas will be much slower. And it makes sense because chlorine is a heavier gas. The effusion rate for the chlorine gas will come out to 8.84 times 10 to the minus 4 liters per second. And so what we're able to see here is that different gases do have different effusion rates based on their molar masses. And as a result, if you had a mixture of helium and chlorine gas, you could separate that mixture by doing an effusion process, because the helium will effuse into the evacuated part of the container much faster than the chlorine. And so that's how you could work to purify and separate the two gases out from one another. That brings us to the end of this video. And up next, we'll talk in more detail about collisions between gas molecules.